Previously, we were discussing about the learning rules, correct? And we discussed about the various aspects of learning rules by considering one of the learning rule, correct? That is a Hebbian learning rule. And we also have discussed about how the learning of ANN matters, right? On what all aspects it's going to depend upon, right? So those were the topics we were considering earlier. Now, as an example, we'll consider another learning rule just to make sure that each learning rule is different, right? Okay, so this particular learning rule is called as the perceptron. The perceptron learning rule. Okay, so let's quickly go through the steps, and we'll utilize those steps and we'll solve some problems at a later stage. Okay, it's a algorithm that basically defines the learning using a different technique. Okay, so the first step in this particular learning rule is always initialize the weights and bias to equal bias to be 0. Okay, so this is initialize the weights and the bias uh, to 0. And now you see we need one special value, right? Define a threshold theta. Okay, we have to define this now. Again, we are free to choose what we want here. Okay, specific value of theta can be uh, selected, right? Then the second thing to initialize is what is the learning rate, and we'll see the effect of learning rate later, but we define the second term here. This is set the learning rate alpha. It's the notation, it should be, say, between 0 and 1. Normally we try to keep it between 0 and 1. Then the third step is to calculate the output, that is z equal to the bias plus the summation over all the possible values of I. I'm supposed to perform xi into wi, right? Then the fourth step is to calculate the output of that neuron which we are considering, which we are giving the input. Okay, so calculate the output of the neuron, right? That is y is equal to sigma of z. Now we define the sigma in slightly different fashion compared to the previously defined uh, activation functions. Okay, the activation function used for this perceptron learning rule is not any of the previous techniques. Okay, previous activation functions. So this is going to be 1, right, if the z value is greater than the defined threshold. This is going to be 0 if minus theta less than z less than theta. If the z is between the positive and negative values of the theta, you are going to restrict the output to be 0. And this is going to be minus 1 provided the z is less than minus theta. So see, there is a slight difference in the definition of the activation function for this case. Now let's look at the plot of this activation function, right? So this should be z, and let's say this is a sigma of z. So let us assume that we considered two theta values. One is the plus theta and one more should be the minus theta, correct? And we want the values to be 1 and -1, correct? So at a point where it is z is equal to or greater than theta, I need a specific value. And also where this meets -1, I need another location. This is because now you see, I'll plot the activation function. So this has to be 0 whenever z is between minus theta and plus theta. So this is the line. And let's say I'll plot this. Okay, so it is above theta. So whenever the value is more than theta, this has to be like this. And whenever means it is 1, right? And whenever the value is less than minus theta, again you see that it has to be like this. And we'll make a connections just to so this is one location, and on the other location also we'll make a connection. Okay, so you see, this is the activation function that is required for the perceptron learning rule. All right, once this is done, we move on to the next step. So previously we have seen that we have step number 4. This is the fourth step, and the step number 5 is like this. Now I have to compare this output y with the target, right? So if say the target is let's say define this is t is not equal to y, in the sense the y which we got in the previous step, it's not same, right? And I have to check another condition, the input xi is not equal to 0, right? If this is the condition, you update, right? So if this is the condition, then only you update, otherwise there is no way to update. Okay, so then update weights. So how do you update the weights? The wi plus 1 is equal to, this is wi, right? Wi is the current weight plus alpha times the target into the input, current input, that is xi. Okay, old one, and you are going to use this, right? So then I'm going to use the equation for bias. So this is bias b is equal to, I can write bi plus 1 is equal to, so this is okay, I'll make a change here. Please make note, this is I plus 1 because uh, wi depends on old values of w plus alpha into t into x, I plus 1, right? So you see xi is not equal to 0, then only I'm using this, because if xi is 0, this term becomes equal to 0. Even I can write as I can simply write xi itself, doesn't matter. Okay, right? So bi plus 1 is bi plus simply alpha times t. T is the target. Okay, so that's what is the meaning. Now you see, if xi is equal to 0, if xi is not equal to 0, then you update the weights and bias like this. So, and say if I have a condition saying that xi equal to 0, then no change in the weight. Okay, so wi plus 1 is wi, and bias I plus 1 is simply bi. right? So this is the learning rule. Repeat this as you give different types of inputs. When we give different inputs, right, we try to date the weights and the bias, and we'll check that what's going to happen every time. Okay, so that's the rule. That's the algorithm which has 5 different steps to be applied. All right, so let's go to one question. This is example. So we'll start with the simplest case, that is uh, develop an AND gate. This has to be performed by using perceptron learning rule. Okay, so again we are going to solve this using bipolar, because it's very clear that the perceptron learning rule uses -1 and +1 at the output, correct? So 0 is intermediate. So what we are supposed to do is that the extreme outputs are +1 and -1. So what this is what is the required table, right? So we have x1, x2, it's the input, and let's write a target. Correct. So x1, when one, we can have 1 1, -1 1, we can have 1 -1, and -1 -1. So when both are 1, both the inputs are 1, it target is 1. In any other case, we are expecting the target to be -1. Okay, so this is the required truth table. Okay, on one side we have the inputs, others the t is the target, which is the output. Now the rule says, according to this, the step number 1 says that initialize w1 equal to w2 equals to 0. Put the bias b is equal to 0, right? Take alpha between 0 and 1. I want to make it as simple as possible for the time being. I'll keep it as 1 now. Anything between 0 and 1 is fine. This is a simpler problem compared to the real world problem. So we can keep it 1, it still learns. Okay, but sometimes you need a value which is closer to 0.5 in practical cases. Okay, just remember, you can make a note of that. All right, then now actually the theta value what we choose here, right? It basically depends upon the complexity, right? Now we have say we have only 2 cases here in the output, right? In the meaning, either I have an output which is +1, or I have another output which is -1. So whenever the output classes are restricted to 2, right, you don't have to assume a theta. Again, this comes from practice, right? For the time being, you just remember, right? I'll just write theta, I put it as 0. I'll write a reason below this. Okay, this is because, right, only 2 classes. What are the 2 classes? +1 or -1. I just have only 2. I don't need a 0 in the middle. Okay, that's the reason why uh, we are making theta to be equal to 0 in this case. Okay, so once you initialize all of them, look at the rules to be followed. So calculate z is equal to b plus xi wi. This is the next case, for which I need to give the inputs one by one. So the meaning is that initially I give this set of inputs as first inputs. I calculate, I update the weights if needed, then I give this as input. Right? Once again, I check the output. If it is needed, I will update the weights. Otherwise, no problem. Then give the next one. Once again, required output, and do this and keep updating. Right? Once the 4 steps are completed, 4 inputs are given, you can check that what are the weights you have, and you can try to build the classifier by drawing a straight line over the space, and you can check that whether the weights at the end of the training is sufficient to classify or not. If it is not sufficient, you may repeat the process once again. Okay, so you may repeat You may repeat the whole process of what you call training by giving the same set of training data once again. That is possible. All right. Okay. Now, so this is the first we call once you give all the four sets of inputs and then you repeat the four inputs once again, it is called as an epoch, right? This is epoch, epoch 1. Epoch 1 indicates that for the first time I'm giving the four different inputs, right? This is epoch number 1, right? So what is your input? Input is 1 comma 1 in the sense, out of the four sets of input, I'm giving this as an input and this is my target. When I give 1 1, I'm expecting the machine to give an output equal to 1. Okay, so this is the x, and let me write the target. Okay, and what is the target? And target t is equal to 1. How do you know? From here, from the table. Okay, now the rule says that calculate the z value, right? So how to calculate z? Z is equal to, this is the bias value, plus summation xi into wi. So in this case, I am supposed to perform b plus x1 w1 plus x2 w2, isn't it? So this z I will calculate. What is the bias? Initial value 0, right? Plus I know that x1 is 1, but the weight is 0. Plus 1 into 0, z becomes equal to 0. Okay, now y is equal to, let me make it, this is sigma of z, correct? So sigma of z means z is 0, this is equal to 0, right? Why? Because I'll write the modified y now. So sigma of z equal to, because now you see the theta has reached 0 itself, correct? Now theta is 0, so because of which 1, this sigma z is 1 for z greater than 0, this is 0 for z equal to theta, theta is 0, okay, and this is minus 1 for z less than 0. So this is the uh, modified sigma that we are going to use here. Okay, now let's use this. So 0, this is equal to target. No, this is not equal to target. Compare, target was 1, but now I got the y as 0, which means machine has to learn something now. The current values are not optimum. So whenever uh, the y is not equal to target, you need to update. Okay, so let's do the updation. So what's the equation? Weight wi plus 1 is wi plus this is alpha into t into xi, correct? So I have to perform both of them. So w1 I'll update. W1 is equal to, what's the old value? 0, plus alpha is 1, target is 1, and input is also 1. So this is 1 now. Similarly, w2 is equal to, old value of w2 is 0, plus alpha is 1, target is 1, and even the input is 1. So you see this is equal to 1. Okay, and let's update the bias. So b is equal to old value of bias, that is equal to 0, plus alpha into t, right? So this is also a 1. So you updated now. So now onwards you are going to use w1 is equal to 1, w2 is equal to 1, and bias equal to 1 for the next process. Okay, right. Now what we do, we'll give the second set of input. So what is that second input? The input is, from the table I give minus 1 1, so this will be our x, and what is the target? For this the target is minus 1, isn't it? Right. So how do you do? First we determine whether I need to update the weights or not by calculating is z. Z is equal to b plus summation over I wi xi. So bias, you can see previously updated bias is there. This one will be used over here. Okay, we use that. Then this is 1 plus, individually I am supposed to substitute. Xi is first value is -1, but the weight is 1, plus the second input is 1, weight is 1. So they will cancel, the answer becomes 1. Right. Now I use this. So the y is equal to sigma of z, that is sigma of 1. So sigma of 1 in this case, is it 1? Yes. Right. So whenever this is 1, my target is -1. So this is not equal to target. Correct. So see, the target is -1. And right now I'm not getting that. So it means I need to update. I have to show the update now. Okay, let's do that. So weight, I'll directly do this calculation. So W1 is equal to old value, which is 1, plus 1 is, this is alpha, target is -1, and even the input, first input was -1, right? So this is -1 in -1 plus 1 plus 1, so 2. W2 becomes equal to old value 1 plus alpha into target into second input. You look at the x2. X2 in this case is +1. Okay, so I write 1 over there. So this is 1 minus 1, 0. Then I have to update my bias, right? Old bias plus 1 is the alpha into target is -1. This becomes equal to 0. All right. Okay, once we do this, we have updated the values. So this means I can give the next input. So give the third input. What's the third input? If you check that, third input is 1 minus 1 from the table. And what is the target? -1. Okay, so this means I have to calculate, repeat the steps with these values. So z is equal to b plus summation xiwi. Okay, so what we do now, how do you calculate? So the bias, you can see bias is 0, previous bias, plus uh, it's wi into xi. So w1 is 2 and the input is 1, plus second one is 0 into -1. So this is, now z is equal to 2. So y is equal to sigma of 2. So it's greater than 1. So 1. Correct? So again, I can see that this is not equal to target. Current target is -1, but I am getting a +1, which means machine has to learn once again. Okay, so this means update. And when my intention is now to update these values, right? So let's do this. So W1 is equal to initial, the current value is 2 plus alpha into the target into the input. First input is 1. So 2 minus 1 is 1. Okay, then W2 is current value 0 plus alpha into target into this. So minus into minus is plus. My answer is 1. Are you okay? Then, okay, I'm updating the bias. So B is equal to present value 0 plus alpha is 1, target is -1. So this becomes -1. All right. So for the third third set of inputs, we have updated the weight. So let's go to the fourth input. Right? So the fourth input is, give the input as -1, -1. And what's your target as of now? So for this input, the target is -1. So calculate Z, which is B plus summation WI XI. So bias is -1, okay, plus input is -1, weight is 1. So this is -1 into +1 plus second bias is also, sorry, second weight is -1, but the input is 1. So -1, -1, -1, -3. So how do you calculate output? Y is equal to sigma z, right? So that is sigma of -3 less than 0. So this is -1. So you can see that it is matching the target. So you can say that for this input, the machine has learned how to classify. So whenever -1 gives, machine directly gives you a answer saying that, yes, it is -1. Okay. So now you see, in the sense, when it's as of now, it is working for one of the input. Okay. One of the input, that is -1, -1. So I completed the training as of now. First set of training, first epoch is completed. Now what I'm supposed to do, I have to check that whether with these weights W1, W2 and the bias, uh, are we able to classify using this particular machine? I need to check that. Okay, so at the end of first epochs, the weight W1 is equal to 1, W2 is equal to 1, and the bias B is equal to -1, isn't it? Now we know there is one equation of the straight line which we can directly develop. Okay, so let's do that. Let's check that first. So the straight line equation, we know that in terms of x1 and x2. So x2 is equal to minus of w1 by w2 times x1 minus b by w2. This is the standard equation which we already have derived. So this implies, try to write the equation now. X2 is equal to minus, what is W1? W1 is 1, W2 is also 1 times x1 minus, what is B? B is 1, B is -1, sorry, B is -1 and this is 1. So I can understand that x2 is equal to minus x1 plus 1. It says that, okay, this is the as of now. So when first set of inputs are given, right, this is what the machine has learned. Okay, now let us try to identify whether this is classifying correctly or not, right? For which we have to go to the coordinate system. We have to draw a graph. Okay, so this is say x1 and this is x2, and as of now, what are the coordinates of inputs? One class, when both of them are 1 comma 1. Okay, first let me write the values. This is +1 and say this is -1. Along the x-axis, this is +1 and let me say this is -1. So I know that these are the required points. Okay, first point is this one, and this has the values 1 comma 1, and the other 3 points are actually falling onto the other side of, or the other class. So this is -1 comma 1. So this is the next point, which is -1 comma -1, and this point is 1 comma -1. I know that they belong to different classes, so I plotted with different colors. But now let's check, right? How to check what is that, whether the line is classifying or not, right? How to check that? We just have to identify where the line passes through which points. We can find any 2 points. Okay, so that is, if let's say x1 equal to 0, when x1 is 0, x2 equals to +1. correct? So this means the point is 0, comma 1. So where is the point 0, comma 1? That is here. Okay. This point is actually 0. I'll write on the other side so that it will not overlap the straight line. So this is 0, comma 1. And let's do the other way. Let's make x2 equal to 0. This means x1 is equal to 1. So the point is 1, comma 0. So the straight line actually passes through another point, that is 1, comma 0. So this is 1, comma 0. So through these two points, now I am expected to draw a straight line, right? So it is very clear that the machine is able to classify. You see, this is class 1 and this is class 2. Correct? On one side of the line I have one point which is actually corresponding to one of the point, and the other side we have 3 points which are belonging to the second class. So this indicates that yes, the machine is learning, machine has learned. So now if at all machine has not learned, what is expected? You go for the second epoch and continue training.